Okay, so welcome everybody to the extremely exciting second week on elliptic curve cryptography. So what we did last week, even though it seemed like a lot of material, what we really did, we essentially introduced one more cyclic group, and we mainly talked about this elliptic curve group operation. So what we want to do today is we want to essentially do two things, and each of these things are a little bit more complicated because elliptic curves are complicated. We want to talk about elliptic curve discrete logarithm problem, which I think is a pretty cool idea. And then we want to put things a little bit into practice and demonstrate a little bit what we can do with elliptic curve. And we picked the most simple protocol, which is elliptic curve Diffie-Hellman. Okay, so two things: discrete logarithm problem, Diffie-Hellman. What is nice about this whole stuff, as you saw, elliptic curves are pretty complicated. What I like about today's lecture, we essentially do the same thing we did over the last 4 weeks or so, namely talk about discrete logarithm problem, but with a different structure here. So we combine this new weird things, elliptic curves, with something we did before with respect to the discrete logarithm problem, one-way functions and stuff. And secondly, again, we take this new complicated stuff and somehow relate it to Diffie-Hellman. And what I hope is also that you get a better understanding what is a discrete logarithm problem, what is Diffie-Hellman really. Okay, so I think from a pedagogical point of view, this is hopefully a useful thing that we're doing today. Okay. So, first chapter of today is, again, EC by itself stands for elliptic curve, and if it's ECC, it's elliptic curve cryptography. So this is elliptic curve discrete logarithm problem. So what we showed is, if you consider a certain type of equation over the real numbers, we get this type of curve. And then what we did, this kind of repetition from last week, and then given 2 points P and Q, we came up with this weird thing doing addition. And this is, what you suffered through last night when you started working on your homework, right? We did group addition. P plus Q. So, and now, we ended last week at the end saying they form a cyclic group. Okay, and that was just a theorem, and you did your homework, but I want to do that together with you one more time to put a little bit life into that whole thing. By looking at an example. I really want to look, is this really a cyclic group for one specific example? Okay, we look at an example, elliptic curve as a cyclic group. And again, in your lecture notes, this should be immediately under where we stopped last Wednesday. Okay, because the last theorem was under certain condition, elliptic curves form a cyclic group, and now we look at an elliptic curve that actually is a cyclic group, the points of which are a cyclic group. So very often in literature, you just give a name to this equation. It's typically called E for elliptic curves. So the curve we're looking at is exactly the one that we're using in our textbook all the time. It's y square is equivalent to x cubed plus ax plus b, and a has a value 2. So x cubed plus 2x plus 12 the modulus, the prime that we consider is 17. Okay. And now comes an important remark. For this specific curve, all points form a cyclic group. Which is not always the case, but this is an easy case here, from a teaching point of view. That's why we picked that curve. And now we want to really look at the cyclic group. As I said last week, what is the requirement for cyclic groups? It's a very, very simple requirement. What kind of thing do we need to have for a cyclic group? I'm not continuing until I hear an answer. What's that? Ein Generator, genau, a generator. So, and this generator, another word for generator is primitive element. The primitive element is, for instance, there are a whole bunch of primitive elements, but we look at this primitive element, p equals to 5, 1. So the x coordinate is 5, y coordinate is 1. Okay? What is a generator? What is a primitive element? If you take the powers or the multiples in an additive group, if you keep adding p to itself, you generate the entire group. And what we also did last week, actually for this specific point and curve, we computed 2p, which is p plus p, and it turned out. This is last night, right? 11 p.m., right? 23 Uhr, when you did your homework, right? This is the stuff here. So this is this complicated formulas, right? With the s, the slope, and so forth. So this is, turns out, and there's the dots here, so this is not non-trivial, right? This, if you do the pocket calculator, it takes you 5 minutes to do that. Then we can do 3p, which is 2p plus p added to again, and again, 5 minutes pocket calculator, and you end up. My mistake here. This is 6,3, and the next point is 10,6. And so forth. Okay, and we're not doing all of that here, obviously, and then. At some point, we hit 18p, which has this coordinate, okay? And one thing, if you look at it, what happens is you see this x-coordinate and this x-coordinate are the same. And there's actually more happening, namely, did anyone know how the 16 and the 1s are related here? They're the inverse modulus 17, right? With the coordinates itself, we do this modulo p arithmetic. So this is the same as 5, minus 1. You take minus 1, you add 17, you end up with 16, right? This is in Z17, right? In Z17. So, but this is the condition. So what is this equal now to? If you compare those two here, does anyone know what is this here now? This is yep. Yes, exactly. This is minus p. Good that I force you to do homework, right? I mean, I can tell you there's no way anybody would remember that we did that 168 hours ago, right? Or 166 hours ago, last Wednesday, if you hadn't done the homework yesterday or whatever, or 5 days ago. Very good. Super. So, and just tiny reminder. I mentioned that there are two minuses here in this expression, right? There's this minus, which is a minus with respect to modulo 2, and there's this minus with respect to group operation, and they're completely different beasts. Okay, they mean something completely different. They both look like, innocent little bars. They're something completely different. They essentially have nothing in common, just to stress that. So, coming back to our cyclic group stuff, so we've seen 18p is the same as the inverse of p. So, now let's continue this cyclic thing, let's continue adding p to itself. So the next would be 19p. So how do we arrive 19p? Well, obviously we take 18p and we add the point one more time. Okay? And now you have to be careful, and you have to, in this coordinate system, you really have to manually check that you can't use the group equation at this point. Okay, so what you really have to do before you do the group operation, you have to check whether the 2 points that you're adding I'm sorry, it's too early here for me. 5 and 16 plus 5 and 1. You have to check whether the y coordinates are the inverses of each other, modulo p. And they are. And in this case, what is the result? Any ideas? Neutrales Element, exactly, the neutral element. Okay? Which doesn't have coordinates. You don't have to use your pocket calculator, do anything funny here, right? As soon as you see that, the inverse of a point plus the point itself is point of infinity. You can't really do arithmetic. It has to do with the fact that this is this imaginary, imaginäre point. Doesn't have real coordinates. Okay, so this is 19p. So what's going to happen now? We want to compute the next point, 20p. What is that? Well, 19p we've just seen is the point of infinity plus p. And it was really good. Nobody said point of infinity. You said neutral element. And this is exactly what happens here. Neutral element plus p is p again, right? So 20p is equal to p. (21p) is, of course, 20p plus p. But 20p we've just seen is equal to the point itself. So this is 2p. You get the idea, right? I do one more. 22 times p is 21 plus p is so forth. Yep. Probably made a mistake. Yeah. I might have. Yeah, Yeah, so I made a mistake. You see that there? It's +2. The elliptic curve equation is wrong. Get rid of that one. Very good. So, what is this big thing that I want to bring across? The big Lern effect here is after 19 p's, I'm back to the beginning. I'm back to p again, right? 20 times p is equal to p. 21 is 2p and so forth. So I'm starting cycling around, which is this very property of a cyclic group, right? I wanted to show you that here. Okay? What I really... Können wir leise sein, auch da billige Plätze, ja. What I really like about that is that this is so different than looking at cyclic group with integers. You know, looking at integers, saying, well, this is some kind of odd behavior with integer and modular arithmetic. Here, we have this completely pathological, krankhafte group operation, right? This really odd thing, you're doing arithmetic on elliptic curves, adding points, and suddenly we get exactly the same behavior we observe with integers. And sometimes if you generalize things, you get a deeper insight. And I hope this happens. Maybe with the next homework assignment, but it's I like that. I think it's very cool to do. Okay, so again, you see this starts cycling around here. What we really want to do in crypto, why do we do that? We're not that fascinating with, groups with some kind of cyclic structure per se. We want to do something with that. Namely, we want to build crypto systems. Okay? And in particular, we can build crypto systems by looking at certain type of problems. And in this case, with cyclic group, we built DL problems, discrete logarithm problems. And that's what I want to do now. We obtain immediately a discrete logarithm problem, and I'm going to show you that the pages from our textbook, which is definition 9.2.1, on page something rather. Okay, so this is what I want to briefly talk about, and it's almost the same we had before about discrete logarithm problems. So the algebraic structure, that means the set where we do arithmetics that we consider is not mod p, but this is, of course, an elliptic curve, right? So we look at an elliptic curve, we look at a primitive element. Why is there a primitive element? Because discrete logarithm problems, live in cyclic groups, so there must be a primitive element and another element t, right, which is called here, right? And remember, what is the property of a cyclic group? If you have a generator, if you have a primitive element, this primitive element, of course, generates all possible all points, all existing points, including, obviously, the point t here, okay? So that means this point t can, in fact, be expressed as a multiple of the primitive element, right? You do p plus p plus p plus p a certain number of times, and this is a hard thing to figure out, and here we call it d times, and then if you add p d times, d is, I don't know, 5 or 7 or some 256-bit number, it's equal to t, okay? And the discrete logarithm problem is, given p, given t, given this the first point, given the other point, what is the small parameter d, which has an extremely nice graphical interpretation of the discrete logarithm problem, much, much nicer than modulo p. Okay. Which all the books don't tell you, but I do. Okay. So a graphical interpretation, and it's not very deep, of the discrete logarithm problem is if this is our generator, P, kind of our starting point. Okay. And now what we do, we start hopping around, springen, on the elliptic curve. That means we do the group operation. Right? We do P plus, for instance, P plus P, and we end, I don't know what that would be here, would maybe be 2P, and then you do the group operation again, and you would end up perhaps here, you get 3P, and you get 4P and 5P and so forth. You keep doing that, right? And at some point, you stop and you get some final point, maybe here. Get T. How did he get there? Well, you hop many, 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 many times on the curve, right? And now the discrete logarithm problem is the following. Everybody awake? It's 10 seconds, 10 seconds. I give you the starting point, the primitive element. I give you the final point, which is the public key, and you tell me how often did I hop on the curve. The number of hops is what is the number of hops? In cryptographic terms, this is the private key. The number of hops, so the number of group operations that are executed, this D, right? D times. The lowercase d is the secret key. And this is a hard thing. If I give you the start point and the final point, it's really hard to tell how often I hopped around in order to compute that. Okay? Again, none of the books tell you this graphically. Okay? Back to sleep. So looking at this definition here, we can maybe look at the example for the discrete logarithm problem. Let's say the starting point in this elliptic curve we looked at before is this primitive element. Now I give you one of the points, one of these 19 points that are being generated, namely the point T, right? What we do know is, since P is a generator, we know that this is possible, right? This is possible, meaning there exists a D, there exists an integer D, so that this point can be written as a multiple of P, multiple addition. The question is, what is D here, right? It means in other terms here, just to put a little bit life into that, what is D? Can anybody tell me what D is here? It's not 19. Because 19, 19 times P was the point of infinity, and this is not the point of infinity here. This is hard to do. You can't do it even with this small example. You cannot do that. You can look in the book, or we look. We look at this example. We just here. So you have to look at this table that's from the book. If you look at this, can anybody tell me what D is? What the private key is here? We have to look yeah, the C13P, right? So from the textbook, we conclude that D is equal to, what did I say, 13, is that right? Yeah. Okay. So, yeah, another mistake. I'm sorry. Sorry. But very good. Sehr gut aufgepasst. Danke. Of course, P is this primitive element here. Okay, so let's stick a little bit more with this definition. I blow that up again. Okay, so what is very important here from this definition? Again, we looked at it. We saw that first we have this primitive element, which is kind of a little bit boring. But what is interesting is that we have to look at the two type of keys that we have. Okay, namely, note about elliptic curve discrete logarithm problem ECDLP is that D is a private key, and again, D is the number of hops on the curve, and this is the data type. What kind of thing is D? Is that a complex number, or a differential equation, or a matrix, or a rational number, or it's an integer, it's a number of hops. It's wie oft ich gesprungen bin. This is an integer, this is nothing weird, okay? So this is an integer, okay? Very well behaved, and this is true for all discrete logarithm problems. It's always an integer, no matter what curve, what group you're working with. Not so. How did I call it? T, right? This uppercase T is a public key. And what kind of thing is that? What kind of algebraic structure? What kind of data type, if you're more in computer science? What's it? Two integers in this case. In general, this is a point. This is point on curve, i.e. das heißt a group element. And this is always true for all discrete logarithm problems. The public key is whatever weird thing you're using. Okay, this is elliptic curve, so you think this is strange. There are stranger things. Okay, there's algebraic varieties, there are hyperelliptic curves. So there are even wilder type of discrete logarithm problems, generalizations of elliptic curves. The public key is whatever weird thing you're working with. Okay, not so. That means the public key here. Not so the private key. The private key is always so the number of hops, if you wish, the number of group operations. This is always a well-behaved integer. So this is always elementary school, right? This is Grundschule here. This is, you start to count, right? 3 teddy bears, right? How many circles are. You know what I'm saying? So this is nothing strange. This is very often strange. Okay. Okay, so now we have to stick with this weirdness for a little bit longer. So one question maybe is that came, yeah. What is very important if you do discrete logarithm problems in practice? What is very important, one question that you need to answer, and that has to do with attacks. For certain attacks, it's very important to know how many elements are in the group cardinality. Okay, so group cardinality, which is a really fancy way of saying how many points are in my cyclic group, right? This is what it's also called the order of the group. I like group cardinality a little bit better. What is the group cardinality? How many points are on the curve? Okay. Maybe let's go back to this example first. You know, we looked at this specific elliptic curves and we kept adding. This is the example we did. Can anybody tell me from looking at the blackboard, you can see that how many points are in this cyclic group here that we're looking at? 19. Very good. Be careful. You're absolutely 100% right. There are like 18 actual points, real points, you know, P2, P3, P, blah, blah, up to 18 P with actual coordinates. And point number 19 is point of infinity, but this counts, right? This neutral element, of course, is part of the group. Okay? So for this specific group, we have a group cardinality, and there's a special symbol for that. I'm going to introduce that in this second. This is okay. You know, this Doppelkreuz, is number of Anzahl, right? Number of E, this is 19, okay? So this was an example here, okay? So in general, for general elliptic curves, what are the number of points? And there is a very useful theorem by, I believe, a German mathematician. Just went over this. Which is Hasse, okay? Hasse theorem or Hasse bound or Hasse Schranke, right, in German, Hasse Schranke, which tells us, if you look at an elliptic curve, and this is the case modulo P, you can also do that over general finite fields, but if you do that modulo P, this number here, right, means the number of points is bound, is eingeschränkt. On the lower hand, it's essentially P. You know, you have P here, you have P there, plus, if you wish, some correction term. Okay? Namely, you know, 1 minus Wurzel P, and here you have, or essentially here, you know, minus 2 times square root of P plus 2 times square root of P here. Okay? So, and this gives you a bound, Schranken an. Okay? So, Hasse theorem gives us a lower and upper bound for E. Okay. And this is, what is that? Compare theorem 9.2.2 from the textbook. what in very engineering-ish, very rough terms, what this tells us, very rough approximation, heißt Annäherung, Schätzung, Näherung, approximation. Continue underneath here is number of point is roughly, very, very roughly p, okay? If I see critical phases in this room, this is great, because if you look at this expression here, it doesn't seem that E is that close to P. There seem to be all the square roots going on, blah, 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 blah. But what we're really seeing up there, what the Hasse point really says is E is in the range of P plus 1, which is P, this plus 1, we don't worry too much about it, plus minus square root of P, okay? So what this really tells us, a number of points is the prime itself, and then plus minus, we go in direction of 2 times the square root, okay? Square root still looks big, and can be, in absolute terms, this is a huge number. Also the Absolutwert is gigantic. The relative value, relatively to P, is small. To give you an idea, what is popular is P, for instance, as a 160-bit number. I'm going to talk more about 160 bits in a minute. How many bits are in P here, in square root P? Wurzel aus P. Yep. 80 bits. If you take the square root of a number, you have the number of bits, so that means okay. So what's, and then factor of 2, what happens with the bit length if you multiply a number by 2? By 1 bit, right? You double, so this is 81 bits now, okay? This is okay. So what Hasse's bound tells us is very engineering-ish, second semester. We have a 160-bit number, and the maximum what we do, the maximum derivation, Abweichung of this p-value is you add or subtract 80 bits. That means you add or subtract something here kind of in the lower half, okay? To put things into perspective, this is the same. You do Wer wird Millionär, right? You win this 1 million, and the correction factor is square root of 1 million. What is the square root of 1 million? 1,000, right? So you win 1 million, and this is plus minus 1,000. If you win 1 million euros, it's essentially you don't care whether you will win 1 million, 1,000, or what is it, 999,000 euros. Everybody with me? This correction term of square root p is pretty small. In absolute terms, the Absolutwert is gigantic. I mean, the absolute value is 2 to the 80. It's some huge, huge, huge number. Relatively to a 160-bit number, it's not that huge. Okay? So why this is not such a bad approximation. So, but things are actually not that pretty. As I make it as I made it sound here, okay? In reality, things are a little bit more difficult because in practice, one needs the exact number of points in order to thwart abwehren. Ist wahrscheinlich ein neues Wort für manche. Thwart ist abwehren. To thwart certain attacks. Okay? It means it's great that the Hasse bound gives us a rough idea, which is very important. You know, we want to know how big this algebraic structure, how big the discrete logarithm problem is for some attacks. You know, you need a minimum size, for instance, to protect against brute force attacks and square root attacks. But for other attacks, we have to know exactly how big the elliptic, what the cardinality is. We need to know that exactly. And Hasse's bound doesn't give that to us. Hasse's bound only tells us, 160-bit plus minus a correction factor, and we need it, down to the little last bit. We need the exact number, and this is unfortunately hard to do. Finding number of points exactly is computationally difficult. And I'm not going to talk about that, how we do that. I mean, this is pretty advanced number theory, how to find the number of points. If you get really frustrated, as soon as we want to use it, Professor Parr doesn't tell us the whole truth. This is so hard. It's not that so hard, and there's libraries out there that compute that. But very often in practice, because this is hard, people use standardized elliptic curves. There's standards out there. There's a very popular standard by the American standardization body, NIST, which many people use. That we call them the NIST curve, N-I. National Institute for Standard and Technology, I think is the abbreviation. So they're called the NIST curves. They are about, 14 curves or something, okay? There's also the German BSI, the BSE also proposed curves. They're secure, and for these curves, you have the number of points on the website. I think even there's a Wikipedia entrance, English Wikipedia. For the NIST curves, and he finds the curves, that means he finds the coefficient A and B. Where is that? Somewhere here. Do we have A and B? No. You have A, B, and P, so you have the 3 parameters. You have some other parameters that we haven't really introduced here. And you have the cardinality, okay? Because it's pretty hard, and you use the standardized curves and then start building your from that. So we have one more thing in order to finish this first chapter. Namely, we want to look a little bit again at this discrete logarithm problem. On this lower definition there, namely all elliptic curve protocols such as Diffie-Hellman, which we're going to do in 5 minutes, rely on the hardness of the ECDLP. Again, what does this mean, rely on the hardness? Beruhen auf der Schwierigkeit means if you want to break that protocol, if you want to break Diffie-Hellman, if you want to break elliptic curve digital signatures, you have to solve this problem. And then hardness means hopefully that's a hard problem. Hopefully that's really difficult to compute. With all supercomputers on planet Earth, this cannot be done, hopefully. Okay? And the question, how hard is that? And I just want to talk a little bit about that. So the question is, how hard, how difficult, wie aufwendig ist das, ja? Ja. Ja. Kurven. Da gibt es nicht genug Tinte auf der Erde für. Das sind ja 260 Punkte, das ist wirklich, da gibt es nicht genug Tintenatome. Das geht nicht. No, otherwise you could do a brute force attack. That's a good remark. No, he had a good question. He said, so with the standardized curves, is there everything given? Is the primitive element given? Yes, of course. Does this help us with attacks? That's maybe what you were thinking of. No, of course it doesn't help us. You have a primitive element. What the standardized curves do, they essentially give you the curve. I mean, you never see a drawing, obviously, but you essentially have the curve, you have the starting point, good luck, right? From there, whatever app, you have your new iTunes, your new apps that you write with some security property, and you want to make money with your app. You take the curve, you take this graph, you take the generator, and from there you're on your own. You choose a random D, you end up with your public key, you have a private key, you can build your crypto system from that. And the attacker, and that's kind of the interesting thing, the attacker doesn't have any advantage from knowing the curve ahead of time and the point here. You can't pre-compute all points. I mean, if you could do that, you would have a brute force attack. Okay? So, how hard is it? And we did talk about that a few weeks ago before... No, I think two or 3 weeks ago when we talked about the discrete logarithm problem, we talked about the attacks, and maybe that seemed a little bit abstract, and maybe you get a little bit more feeling for that now. Namely, long story made short, the discrete logarithm problem is very, very hard. So this is good for us as a designer. If you design crypto system, we're not the cryptanalysis, we're not OSCAR, we don't want to attack this, we want to build something secure. This is a very good situation here. If the elliptic curve EC is chosen carefully, that means you have to be careful with a lot of things, and this is why people use the standardized curves. They're chosen carefully, so they checked all kind of mathematical properties. If the elliptic curve is chosen carefully, the best known algorithm for computing the DLP, or the EC DLP, if you wish, or DLP, requires approximately square root of p steps. Okay? And this square root here, just to warn you, this square root has nothing to do with the square root in Hasse. I mean, it's the same number, but there's no mathematical reason why they're the same, okay? So this comes, they pop out of whatever the best attacks are, which we actually, when we classified them 3 weeks ago or so, we called these the square root attacks for that reason, because they have a square root complexity. And it's a sheer coincidence that this is the square root also comes up in the in Hatz's theorem. Again, let's look at an example. If you consider an elliptic curve with a 160-bit prime, that means all arithmetic is done with 160-bit arithmetic. numbers, 160-bit numbers, then the best known attack requires square root of p, which is square root of 160. You remember that, right? 9th grade or so, right? Steps. This is very hard. Actually, Professor Gunesu showed you the Copacabana here, the first lecture, is that right? In way back in October, right? And actually his master thesis, his Diplomarbeit, whatever, 5 years ago, of Professor Gunesu dealt with implementing this best known attack for elliptic curves on Copacabana. Okay? So what you can do with, with the best known, with this custom hardware, I think we can solve 2 to the 35 or something, right? You can do 2 to the 35 operations in 1 year or something like that, right? And from there, we can approximate how long it will take to 2 to the 80. And it turns out with current hardware, it will be 1 million years or something, okay? With the hardware becoming faster and faster, with Moore's law, we can approximate. Rough estimate is 15 to 20 years, okay? For this, for 2 to the 80, we can 2 to the 80, this type of hopping around. I mean, that was his master thesis, right? We can probably do, our assumption was 1 million euros. So we can go to Aldi, not Aldi, but you can go to a store and buy computer hardware for 1 million euros. And if you do that not today, but if you wait 20 years, you buy computers for 1 million euros, you can do 2 to the 80 group operations and this baby is broken, okay? And this is why 160 people say, well, you have a security for 15, 20 years, something like that. This is kind of the lower threshold what people want to use. And actually most commercial products now, they switch to 192, 256. These are 2 other popular numbers. Okay. Schwere Geburt. So, we're done with the first chapter of today. Okay. So now comes kind of a fun part. And what's a little bit a shame here is actually about this part of the lecture. I think what is really good, hopefully, that we generalize the discrete logarithm problem to elliptic curves, as what I said before, in terms of deeper understanding, maybe also Erkenntnisgewinn, maybe that helps you. What's a little bit a shame that there's a lot of mathematics that are really deep, pretty advanced, so there's no, we don't really want to talk about where Hesse theorem stems from. We don't really want to introduce a discrete logarithm problem attacks. So a lot of things where I just give you facts. Einfach Faktenwissen, right? These are, just give it to you, which is a little bit frustrating for me as a teacher sometimes. So now the second part will be different. We look at elliptic curve Diffie-Hellman, and this is much more algorithms, and we do real crypto. So it's kind of a nice mixture, hopefully, in today's lecture. So the second part of today deals with elliptic curve Diffie-Hellman key exchange. Which is sometimes, not always, but sometimes abbreviated as ECDH, if elliptic curve Diffie-Hellman. Okay? So now it becomes, hopefully you start appreciating this beauty of discrete logarithm problems, because all the discrete logarithm protocols look very much the same. Once you give me a new cyclic group, and we have a new cyclic group, namely elliptic curves here, you can just go back to the stuff we did actually before the vacation, in February. Look at the Diffie-Hellman key exchange, and they do exactly the same protocol, exactly the same, just with elliptic curves. So once you have a new group, we immediately have all the crypto applications. We immediately have the key exchange. Later on, we will have automatically digital signature. We have encryption schemes. El-Gamal encryption, you can also do with elliptic curves. It's a little bit tricky, but it's essentially the same. So this is straightforward. Straightforward is one word, by the way. This is very popular mistakes in the bachelor thesis. Straightforward adoption of Diffie-Hellman in ZP. Okay, in ZP, this is the Diffie-Hellman with integers that we've done again in February and actually used a few times so far. Okay. So, for the protocol, we have, as always, we have two phases. We have the setup phase where we need domain parameters, and the domain parameters with the planar Diffie-Hellman were very easy. They were just a prime p and a primitive element, and it's the same here. But we don't have a prime anymore. Well, we have a prime, but we need the algebraic structure. We need the cyclic group. In that P stuff we did in February, the algebraic structure is given by P, right? If I give you a prime, you immediately know what the P is, right? If the prime is 31, well, the algebraic structure is Z31. But now, the algebraic structure is this baby here. So we need an elliptic curve. This is E. Again, which is given by the curve equation, obviously. Okay. And we need a primitive element. So and then we have to run the protocol, okay? First phase, second phase is the protocol, the actual protocol. How does this work? Wie viel Platz brauche ich denn hier? Let's try to squeeze that in here, okay. No, let's not try to do that. Second phase is here. So if just continue underneath here, right? If you're copying this. So we have our parties, Alice and Bob, so here's the story. Alice and Bob have AES, really fast AES implementation. AES is really secure. People cannot break that. And they do some, illegal downloaded videos, right? So they just got this new Hollywood hit and they want to send it over the network and they want to encrypt that. They want to use AES with 128-bit key. So they need to agree on a key and, Alice lives in Bochum and Bob lives in Munich and they don't want to, travel down by, with a Bahncard 50 or something, right? It's really expensive and hard. So they want to exchange a key over an unsecured channel. So Alice and Bob took my class, so they know how to do that. So the first thing is they agree on an elliptic curve and they might use one of the standardized curves, right, that exist. What Alice then does is she has to set up a discrete logarithm problem. What is a discrete logarithm problem? is this here, right? Alice has to do this kind of thing here. Okay? So the first thing she needs is the private key, which we denote by lowercase. So this is k private of Alice, which is lowercase a. K private of Alice. Where do we typically get a private key from? How do we generate a private key? Very broad question. Random, right? Zufallszahl. You don't want to do anything kind of computation that maybe Oscar can compute. You know, and the more random, the better. Okay? So, some kind of random number. And so often you don't want to use if you use the full cardinality here, cardinality of E, if this would be A would end up be the neutral element, which is something you don't really want to do. Bob does the same. Bob computes his private key. Okay. So now we have the private key, which we called D here, right? Now you have to compute your public key, which is called the T value here, which we call uppercase A and uppercase B. Also, yeah.
Wasn't there some restriction that P is greater than 3, I think? A and B can...
P größer 3 ist? Oh, yeah. No. But this is not related to this P hier. Das kommt ja nur aus der Gruppe raus. Also das 2 würde ja einfach heißen. Das hier. Das wäre ihre Verschlüsselung sozusagen. Das ist eine gute Bemerkung. Also die 2 hier, die hat nichts mit diesem P zu tun hier. Also das ist ja, wie gesagt, das ist ja nur, wie oft wir rumspringen. Ne? Das hat nichts damit zu tun, dass wir nicht die Primzahl 2 nehmen. P ist in der Praxis gigantisch. Also P ist zum Beispiel eine 160-Bit-Primzahl hier. A könnte man klein wählen. Aber der muss zufällig gewählt werden. Also die Wahrscheinlichkeit ist ziemlich klein, dass wir da jetzt 2, 3 oder irgendwie sowas haben. Aber prinzipiell vom Protokoll ist gute Bemerkung. Können Sie haben's. So, he was worried that can we choose 2? Is that a problem? Because in the definition of elliptic curve from last week, you really paid attention, it says P can't be 2, but in theory at least you could choose 2 here and everything would be fine if you're Hellman-wise. So this will become our public key. What do we do? Well, you do it's called a point multiplication. So you take private key times primitive element. And again, what kind of baby is that? What kind of data structure do we get out here? Public key. Is that an integer or point of the curve? Point of the curve. Okay, so this is what I told you before. Where was that? I told you. Why did I write that down? You know what I'm talking about? Links oberste Tafel. Sehr gut. Thank you. Private key is an integer, public key is a point on the curve. Very good. Okay. And this is exactly what's happening. This is a boring integer. This is 918,711. It's some integer number. This is a point of the curve. Same here. And again, this exact analogy what you do with over ZP. Now you exchange your public keys. They're public. You don't have to keep them secret. You can send them over the channel. So what Alice does in order to compute the session key, she takes her secret, her private key, and multiplies that with the public key she receives. And this becomes, she gets one result out, and Bob does the same. Bob takes his secret, his private key, multiplies that with the public key of Alice, and surprise, surprise, he computes the same point. Okay? So that's Diffie-Hellman, just to motivate it a little bit more. What we can do at this point is, if we want to actually do encryption here, what we can do now, let's say we have a message M. This is your illegally downloaded video file, right? 1 gigabyte. Okay, you want to encrypt. So, so your AES encrypt M, which is not the hard part, that's the easy part. The hard part is which key are we using? You can use either the X or the Y coordinate. And actually in practice, usually that's too long. For instance, X would be a 160-bit number. AES only needs 128 bits. So what you do, you just take the 128 leading bits, and you drop the other 32 bits. Nur die führenden oder die auf der anderen Seite or some, you have 160 bit, you have 160 bits here, you choose 128 bit. And in practice, it's even a little bit more complicated. Typically, it's recommended to hash that, but I don't want to go into that. So for you, just choose any 128 bits, and we just write that this way, right? We pretend XAB is 128 bit. You get your ciphertext out, which we call C at this. Usually we call the ciphertext Y, but then you get confused with the X and Y coordinates. You send the ciphertext over the channel, and if Alice receives the ciphertext, she wants to watch the movie, right, that you downloaded. So she has to AES decrypt, run AES in decryption mode. And here's now the beauty. She has the same key, right? You share the same key. Grau ist alle Theorie, right? All theory is gray. So let's look at an example. Oops, okay. I don't even have a keyboard here, so okay. Is this readable? Can you read that a little, the protocol? Ist das lesbar? Hinten, billige Plätze, ja, geht das? Gut, sehr gut. So just to show you here, example 9.8, page 251. It's one of the toy examples that we like. Surprise, surprise, we have the same elliptic curve we've been using the whole time here, right? So we use this elliptic curve. Again, surprise, we use the same primitive element we had before, and now we show how to do an, toy size Spielzeug Diffie-Hellman. Here Alice chooses 3 as a private key, and Bob chooses 10. Alice, computes 3-point-P, which you can look back in the table, right? This is what happens. So 3-point-P is this here. Bob computes his public key, which is 10 times P. And again, you look in the table, you'll find 10 times P is this point. They exchange the stuff, and then here you have to do the group operation. So you do 3 times B plus B plus B. You do 3 times the group operation. You end up with this point with the coordinate 13 times 10. And here's kind of the nice surprising thing. Here we're computing B times, that means 10 times the other public key. So 10 times this here, 10 times this here. And it turns out, they compute the same point. Okay? And now, coming back to our example, you see there you have the same x and y coordinates. It means you could use the number 13 as AES input. Of course, this is only like a 4 or 5-bit number. You don't want to do that with small numbers. But if you do that with really large numbers, it works just the same. Let's talk a little bit more about that. Namely, let's look whether this really always works, the proof of correctness. And again, this is very easy. This is very much analogous to plain old Diffie-Hellman. Alice computes A times B and B was the public key of Bob. Where was this coming from? You see it over there. Uppercase B was lowercase b times P. Which is this due to the associativity. Das Assoziativgesetz gilt here because it's a group. What does Bob compute? Well, Bob takes his public key, his private key, and multiplies that with the uppercase A here, with the public key of Alice. Danke. You get the same result. Again, Assoziativgesetz here. Okay? C'est ça. Das war's. Okay? So, towards the end of the lecture, there's one thing which is, again, which is not complicated and which I think is kind of nice too. You want to talk a little bit about computational aspects. How do we implement that? So let's look at the actual computations that Alice and Bob have to do, the kind of operations they have to do. Well, obviously they have to do the group operation, right? They have to hop around on the curve, and this is what we did last week. This is what you do for your homework, right? You can add points. And we have, remember that there's group a point addition and point doubling? Okay. This is one thing, so we know how to do that. But this is now a little bit more complicated. You have to what's called point multiplication or scalar multiplication, which is something we haven't discussed really. You do A times P, and here do A times B. Bob does the same. So and this is what we do towards the end of the lecture, and this is kind of something that is not really new, but it's kind of nice. question is, how to compute essentially the orange dots. How do we do the orange dots that you see there? Okay. And let's say in general terms, let's call that A times P. The problem is, and I think I talked about it, if not, I'll do that now. There's no natural way, direct way of doing A times P. Okay? It looks like, well, you do multiplication. There is no such thing as you're multiplying scalar by points. This is just the same as doing, and I think I talked about it last time, right? Doing, I don't know, 37 times, okay. They ask you to do that. Nobody thinks, oh, there's some arithmetic operation that does that. We all know, maybe this is, I'll do smaller, to the fifth. You'll see why, because you look at that and you immediately see, okay, this is 37 times 37 times 37 times 37 times 37, right? That means this is just a notation, shorthand notation, right? Convenient notation. Same goes here. Okay, so this is just a shorthand notation for P plus P plus P plus A times. Okay, so was the same, but here, if we have really large numbers, how do we do that? Square and multiply, okay? And here's the beautiful thing. The square and multiply works exactly the same for elliptic curves, but instead of squaring, squaring is, okay? In elliptic curve, squaring becomes P plus P, so this is doubling, okay? Squaring becomes doubling. Multiply was, A times, I don't know, X. This is multiply. In elliptic curves, this becomes add. So square and multiply becomes double and add. So it's a double and add algorithm. Okay? The point multiplication A times P can be computed with the nochmal quotation marks with the double and add algorithm. I give you an example. Okay. So let's say we want to compute 26 times P. And remember when I introduced the square and multiply, I said, well, there's a dumb way of doing it and the smart way of doing it. The dumb way would be to do P plus P plus P plus P plus P 25 times. Okay, 25 times the group operation. It turns out there's a better way. And again, the double and add and square and multiply are identical algorithms. You just replace the operations. And what we did with the square and multiply, we looked at the binary representation, als Dualzahl, als Binärzahl, of the exponent. But now the exponent is this multiplier here. So we have to look at 26 in binaries. Turns out to be the number 1, 1, 0, 1, 0 times P. Okay. Here's the algorithm. And I just give you this one example, and then you look the algorithm up in the book. And again, we derived that more formally before. So let's here we take care of the iteration number of the steps. We start with step 0. What we do in step 0, we compute, p, which is obviously equal to 1 times p. Okay, so we don't do anything here. Okay, now the algorithm starts, and an alternative name actually for square and multiply and double and add is left to right method, because we scan the exponent coming from the left. So, and we're done with this one is fine here. This one is this one. Now we have to look at the next one here. So what we do, step 1a, you double. Okay, so you do p plus p is 2p. Which is this binary representation, which is one double here. Okay. Now you look at the second bit here. Second bit, coming from the left. Is this a 1 or a 0? Oh, this is a 1, right? Unfortunately, right now we have a 0 here, so we have to turn this 0 into a 1. And any ideas how do we do that? We add p. This is 2p plus p is 3p, and it's 1, 1. Okay. Can get your stabilos ready. Okay, we need a lot of colors here. So we're done with the second bit. Now let's look at the third bit. This is iteration 2a, first part of the second iteration. We do again double. We always double. So we have 3p plus 3p is a doubling operation. Gives us 6p. Or in binary 1, 1, 0. So the bit we just generated was a 0 at the third position. It's a 0 here. That means we're done in this operation, in this iteration. And at this point, we're already done with the. Okay, let's go to bit number 4. Again, that means we go to the next iteration, to iteration number 3 or step number 3. Again, we double. 6p plus 6p equals 12p. 12 has a binary representation of 1, 1, 0, 0. Okay. Again, what you always generate in the scalar here is a 0. Okay, we just generate the 0 here. We're talking about this bit here, right? Bit number 4 coming from the left. Well, this is a 1. So we have to flip that. We have to turn the 0 into 1 by adding p. So that's iteration number 3b. This is 12p plus p becomes 13p, which is 1, 1, 0, 1 times p, which is exactly what we want to have. So the pattern looks pretty good. And now we have to do the last bit, bit number 4, number 5, depending how you count. Iteration 4a, we do 13p, we double again. We get 26, which is our Zielnummer, which is exactly what we want to have. And I'm out of colors. I don't know what to do. So I can. Okay. And again, to show you what's happening here is, so, in every iteration we doubled in the beginning. We need 1 more minute here. So it's the same rule as before. Eine Minute noch, eine Minute. Hallo, da oben. Ja, sehr gut. So we always double. If the bit that we are processing happens to be a 1, we not only double, but we also add. So the orange bit, so to speak, this was a 1, that's why we also added. The green, in the green case here, there was no 1, so we didn't have to add. In this red-purple one, we again had to add. Okay, so it's the same algorithm, same complexity. You find the full algorithm in the book. I just wanted to. Here, this is there's the algorithm on page 248 here. Klasse Vorlesung, vielen Dank.